Hey AP, in this video we are going to look at enthalpy. So in yesterday's video we looked at bond enthalpy, which is different than just enthalpy. So bond enthalpy looked at the amount of energy required to break and form bonds. Now we're going to look at compounds as a whole. So we're going to look at the heat content of a reaction in terms of the compounds formed and the compounds reacted together. So we're going to look at products and reactants. The good news about this formula is it's one that's on your formula sheet. So again, under thermochemistry, down here, we've got our delta H is equal to, and this is heat of formation. So heat of formation of the products minus heat of formation of the reactants here. So that one is on here, and this is what we're going to use. It also tells you over here that H naught, that's what the little O is at the top, is standard enthalpy. I think those are the ones that we're going to use. So let's take a look at it. Enthalpy is the heat content of a reaction in delta H naught. That's what this is. And remember, we've been looking at delta H for a little bit, and delta H has units of kilojoules per mole. Okay, so it's important that this is a molar enthalpy, so it's per 1 mole of substance. We have to be careful because sometimes we're not given 1 mole of a substance. So at the end, in order to calculate our delta H, we need to divide by, turn our grams into moles and then divide by that to get it per mole that we have. So HF means heats of formation, which is different. We could have heats of combustion as well, which we'll get to in a little bit. So here's our formula that we are going to use. Let's talk about where does this come from? Well, we can look at energy diagrams and we can look at them in terms of enthalpy. So remember, energy is heat. So we can look at enthalpy in terms of energy diagrams as well. If I have an endothermic reaction, that means that my energy of my products is bigger than the energy of my reactants. That means this number is super positive. This number is smaller. So overall, I'm going to end up with a positive value. Whereas an exothermic reaction would result in a negative delta H because my reactant's energy would be much bigger than my products. So a small number minus a big number would give me a negative delta H. Okay, so I'm decreasing in energy if my reactants are at a higher energy than my products, right? So like this exothermic, we would have drawn before by saying, well, my reactants start at a high energy level, my products at a low one, we've got an activation energy, and we come down. Right? This is our classic potential energy diagram, exothermic reaction. Endothermic, we would have drawn it as my reactants started at a low energy level, my products are at a higher one, have a large activation energy, and they come down. So it would have looked something like so. So that makes sense that my endothermic, my products have higher energy than my reactants. My exothermic, my products have lower energy than my reactants. So in an endothermic reaction, energy is absorbed by the system. So from the system, it comes in to help my reaction happen. Whereas exothermic, energy is released from the system into the surroundings. So energy goes out. Exo is like exit, E-X-I-T. Energy exits or leaves. Endo, N, is like enter. Enter. Energy is coming in. Okay, so that was my tool to remember it when I was in your shoes. We can also look at temperature. Okay, if energy is absorbed by the system, so are absorbed by the system from the surroundings. That means the surroundings are losing energy to the system. The temperature of the surroundings is going to decrease. So you're going to make it's going to feel cold, right? Because the energy is getting pulled from the surroundings, which you feel, into the system. The opposite of that is true for an exothermic reaction. Here, the energy is being released from the system into the surroundings. So it's radiating heat out into the surroundings, and that's what you would feel. You would feel that heat energy, and it would feel hot. So that temperature of the surroundings would increase. We can show this in enthalpy diagrams. So if this is for endothermic, we said that my products are at a higher energy than my reactants. So I'd say that they are increasing in enthalpy, which gives me a positive delta H. Exothermic means that my products are at a lower energy than my reactants. So I'm decreasing in enthalpy to make this happen, which would be a negative delta H. And we can draw out these for multi-step reactions. We could show like, we have our reactant start, we go up to an intermediate, then we come down to another intermediate, then we come up to another one, and then we come down to our products or something. So we could show stepwise, and then we'd say, well, at the end, where are my reactants? Where are my products? What's higher than the other? It's positive or negative. And we'll see that in a few examples in our practice. So again, transfer of energy is super important to enthalpy. Remember that bonds being broken takes energy to do so. They want to stay in their bond. They're at that really low potential energy. So I have to put energy in to break my bonds, right? It's like when you made model kits, when we had the model kits out back in chemistry, and you had to, you put them together and they went together pretty easily, but when you pull them apart, you really had to pull to get those apart. It took energy to break those bonds. However, bonds being made releases energy. They're like, oh, thank goodness, I'm bonded. I'm where I want to be. They release their energy. So again, breaking bonds, endothermic, requires energy. Releasing bonds, endothermics. If I am looking at the universe, and in my universe, I have my surroundings and then I have my system. So your system is like your chemical reaction. Surroundings would be like the water around it that you'd be measuring the temperature of. If energy goes from the surroundings to my system. So my system is absorbing energy. That is endothermic. Okay, and I'm focused on my system. If my system releases energy to my surroundings, that is exothermic. Okay, so it's just another way to kind of think about or picturize, that's not a word, visualize what we're seeing and talking about. So thinking about enthalpy, now thinking specifically about enthalpy of formation, the energy required to make a substance. Well, we have standard enthalpy of formation. Again, that's the little naught, and that has a little F after it to say, hey, that's formation, not combustion. So it's a change in enthalpy when 1 mole of a substance is formed from its elements in their standard state, which means, again, that my units are kilojoules per mole. Okay, super important that it's per 1 mole. So for example, if I was told that the standard enthalpy of formation for this guy, which is ethanol, is negative 279 kilojoules mole negative 1, which is the same as writing kilojoules per mole, right? That's what this negative 1 means. It's down here. This means that when the reaction below is carried out, so here's a reaction, 279 kilojoules of energy are released. So we would show that by saying, okay, heat of formation. Things are formed from their individual elements. So inside of this, I have carbon. The most elemental form of carbon is C. And I have 2 carbons, so I have 2 carbons. Then I have hydrogen. The most elemental form of hydrogen is its diatomic state. So hydrogen, H2, I have 5 and 1, that's 6, so 3H2. Then my final element, oxygen. The most elemental form of oxygen is its diatomic form, so O2. I just have 1, so I'm going to have half. So this is where we can put in our fractions for our coefficients. You'll see that much more commonly here. Okay. So what I'm saying is that carbon plus hydrogen plus oxygen come together to make ethanol. And when that happens, my heat of formation, or my standard enthalpy of formation, releases 279 kilojoules per mole. And this negative tells me the direction that it happens. So in this case, this is that it releases. Okay. So in example 1, write a chemical equation to represent the standard enthalpy of formation of CH3Br. Well, it comes from 3 elements. It comes from carbon. Carbon by itself is graphite, which is a solid. It comes from hydrogen. Hydrogen in its elemental form is H2. And it comes from bromine. Bromine, again, diatomic, so Br2. All comes together to make CH3Br. We're told that this is a liquid. Hydrogen we know is a gas. Bromine, I think bromine is a gas at room temperature. It's a brown gas. brown gas or a liquid? I'm going to go with gas. So we need to balance this. 1 carbon here, 1 carbon here, 2 hydrogens here, 3 here. So I turn 2 into 3. I multiply by 1.5, which we can write as 3/2, or you could write 1.5. Doesn't matter to me which way you write it. Then we've got bromine. We've got 2 bromines here, 1 here. Turning 2 into 1 means that I multiply it by 1/2. And that would be my standard enthalpy of formation. It could have also told us how much energy was required to have this happen, and then I could write in my delta H, but it didn't tell me, so I don't know. There are tables with tons and tons of compounds in them that list their standard enthalpies of formation. For our purposes, 99% of the problems are going to give them to us of the ones that are relevant. We'll see that in the next couple examples. So I didn't give you guys a chart because most people didn't need them. So when we need them, we'll just look them up, which is easier. All right, so going from enthalpy of formation to enthalpy of combustion. So the difference that we see is that instead of a F, we have a C, just denote this is for combusting things as opposed to forming them. So now we're burning them. So this is the enthalpy change when 1 mole of a substance is completely burned in oxygen. We have to have oxygen present to burn something. So, for example, if we're told that the standard enthalpy of combustion of this guy, C2H6, so ethane is negative 1,565 kilojoules per mole, means that when the reaction below is carried out, which we see here, 1,565 kilojoules of energy are released per 1 mole of this being burned. Okay, this is because this is 1 mole. So we'd write this by showing, okay, we've got our ethane, and it is being burned, so 3.5 oxygen makes carbon dioxide and water. So standard combustion reaction, and then we're just adding in our delta H. So my chemical equation to represent standard enthalpy of combustion is C5H12. This would be pentane, because there's 5, and 5 is pent. So we would say, well, if I'm combusting it, C5H12, have to have oxygen present, and it's going to combust into carbon dioxide and water. I would balance this, 5 carbons, so I put the 5 here, 12 hydrogens, 6, 5 times 2 gives me 10, plus 6 is 16, half of 16 is 8. And then I would be told my delta H and its number. So that's all it is being able to denote, hey, if I combusted this, this is how much energy was required or released. Well, what if I wanted to do some calculations? If I was given something that wasn't just formation or combustion, but a regular equation where I'm reacting things together. Let's take a look. So in example 3, the thermite reaction was used to produce molten iron for welding railway tracks together. So back in the day, they would react aluminum with iron 3 oxide, and it would produce so much heat energy that it would melt the iron and it would weld the iron together. So it's a really, really, really exothermic reaction. So we want to calculate the enthalpy change in the thermite reaction given the standard enthalpies of formation of iron 3 oxide and aluminum oxide are negative 823 and negative 1,675 kilojoules per mole respectively. So that means this guy is your Fe2O3 and this guy is your Al2O3. Okay. And then part B, why are no values given for the enthalpy of formation of aluminum or iron? Well, let's answer that first, because otherwise, how do we do this problem if we're only given information about this guy and this guy, or this one and this one? Well, these are in their standard state. And so in their standard state, they just exist. It doesn't take energy to make them. So there's no enthalpy of formation for them. They're just 0 because they exist. So we will write our reaction, our Fe2O3 plus 2 aluminums Al2O3 plus 2 irons. And we want our delta H. Remember, delta H, this a little lower. Delta H is equal to my sum of my delta H of my products minus the sum of my delta H of my reactants. And we have to factor in molar quantities for these two. So we said Fe2O3 was negative 823 kilojoules per mole. We said aluminum was negative 1,675 kilojoules per mole. And then aluminum is in its standard state, iron's in its standard state. So those are 0. So putting this into our equation, products, so the sum of, I just put parentheses around it, we've got 1 aluminum, so 1 times negative 1,675 plus, this is 0, we could still show it, 2 times 0, minus my the sum of my reactants. We've got 1 iron 3 oxide, so negative 823. And then aluminum, which is 2 by 0. So when I add these together, I get negative 1,675 minus a negative 823 gives me a value of negative 852 kilojoules per mole. Okay, and we'll see this written, this gets put at the end of our reaction. So we would then see that the delta H for this reaction is negative 852 kilojoules per mole. Okay. So then B, why are there no values given for the enthalpy of formation for aluminum or iron metal? Well, that is because they are in their elemental state. All right, last question. When 10 grams of sulfur is completely burned in completely burned in air, sulfur dioxide is formed and 93 kilojoules of energy is released. Right, the equation for the burning of sulfur and oxygen to produce sulfur dioxide. Okay, easy enough. We've got sulfur, we've got oxygen. Sulfur is not a diatomic, oxygen is. That makes sulfur dioxide. It's all balanced, so that's awesome. Then calculate the standard enthalpy of formation for sulfur dioxide. So I'm looking to find delta H of formation for sulfur dioxide. And we know that that is the sum of my products minus the sum of my reactants. All right, well, that means I need to know my delta H's for the parts of my reaction. Well, sulfur and oxygen are both in their elemental states, so they're 0. Sulfur dioxide, we were told, was 93 kilojoules of energy. It was formed. All right, well, that's how much was formed from 10 grams. So that's all that we have in here. So right now we have our delta H, but it's really not delta H because it's just Q, right? Because it's not per mole, it's just kilojoules. So right now I'm at 93 kilojoules of energy being released. But I want that to be in molar enthalpy, right? Standard enthalpy of formation. This is in kilojoules per mole. And right now I just have kilojoules. So that means that I have to use my 10 grams, convert that to moles, and then figure out, well, how many moles do I have? So let's scoop this up so y'all can see. I have 10 grams of sulfur, molar mass of sulfur, 32.07 grams per 1 mole means that I have 0.3188 moles of sulfur. And if I have 93 kilojoules for every 0.3188 moles, when I do the math, and this is negative because it's getting released, negative, negative, negative. So that is negative 298 kilojoules per mole. So now I can finish writing my equation for the burning of sulfur by adding in my standard enthalpy of formation is negative 298 kilojoules per mole. And there we go. So we'll continue to practice more of that tomorrow in class.